Hello everyone, we're starting Unit 1, which is Kinematics. It describes how an object moves. We're able to predict and track the motion of an object with just a few characteristics. We'll cover both one-dimensional and two-dimensional motion in Unit 1. One-dimensional motion would just be moving in a straight line, and two-dimensional motion might be something like a thrown ball or a projectile. Okay? We will start to group our measurements into different categories. One of those categories is scalar quantities, so measurements that you can take that have magnitude only. It doesn't matter what direction, so things like distance, speed, time, for example, right? Time just tick, 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 tick. It doesn't matter if it's up, down, left, right, it has no direction. And our other category is vector quantities. Vector quantities have both direction and magnitude. So things like displacement, velocity, acceleration, and weight or forces are vectors. So the direction is going to be important when we deal with vector quantities. Okay? To represent vectors, it's going to be really simple. We're going to use arrows. I think that makes sense. It's intuitive. We can represent the magnitude or how big the measurement is by how large we draw the arrow, right? And the direction of the vector we could very easily indicate with the direction of the arrow. So in this particular case, we have two vectors that are both representing a displacement of 10 meters. So they are equally drawn, they are equal size, the arrows that are drawn, but as you can see, one is labeled negative 10 meters because it's pointing to the left, and the other is 10 meters because it's pointing to the right. Here we have a displacement of negative 5 meters, so that is pointing down in the negative direction, and you'll also notice that it is half the size of our 10-meter vectors. So when you first draw that first arrow, it doesn't really matter how big you draw it. But then once you have multiple vectors and we can compare the sizes of them, it's going to be really important that you keep in mind that the magnitude of the measurement is represented by how large you draw the arrow. Okay? So here's a good example where these two arrows are drawn the same size, and this one is half the size of those other ones. You have 10 meters and 5 meters. Okay? A note about coordinate systems. If you don't mention it explicitly, and I'm kind of talking here for the exam, when you take the AP exam and you're doing a free response question, if you don't mention the coordinate system explicitly, then it's going to be assumed that you're in a regular Cartesian coordinate system where up and right are positive and down and left are negative. We might face some problems where a non-traditional coordinate system would make more sense. For example, for something that's falling. Maybe you drop an object off of a building. It might make sense to call down positive because the object is always moving in that one direction. So what you would want to do on your AP exam, you would want to indicate somewhere to say, hey, I'm choosing down to be the positive direction. You can say that explicitly, or you can very simply just label it on your paper, down is positive. Another place where we might choose a non-traditional coordinate system would be something like a ramp. In a Cartesian regular coordinate system, this is two-dimensional motion. If I put a ball at the top of the ramp and I let it roll down the ramp, it's moving both down and to the left, and that seems complicated. It seems like it's two-dimensional motion, but we know this object is only going to be moving in this direction. So it might make sense for me to tilt my coordinate system so that the positive direction is down the ramp. Again, I would want to say that explicitly or just make a little mark on my paper. Otherwise, if it's not stated explicitly, they're going to assume, that is your grader, is going to assume that up and right are positive and down and left are negative. Okay? All right, some more vocabulary here, distance and displacement. You're probably familiar with the word distance, how far something has traveled. Think about your car. Right in the middle of the speedometer is something called an odometer, and it is the total number of miles that the car has traveled. since it was made. So that is regardless of the direction that it's been traveling in, it is just the total length traveled. Same thing goes with a smartwatch. I have a smartwatch that tracks my steps. And at the end of the day, it says you've done 10,000 steps, and it doesn't matter what direction those were, it was just counting each step. Displacement is a little bit different. Because it's a vector quantity, we need to include the direction. For example, all day long I start at my house, then I go to school, I come home from school, and I go back to my home. The displacement is how far I am from my starting position. So if I've come back home and I'm in my original position, even though I've done all these steps during the day, my displacement overall is 0. Because when I combine all of the steps and the specific directions that I took them in, I ended up back to where I started. So distance is a scalar quantity. We don't care about the direction. We're just counting up every step, the total length traveled. And displacement, because we're including the direction, we're just going to look at the difference between the starting and ending position. Okay? So an equation, very simply, to write displacement, that little triangle there, triangle x or delta x, is just the final position minus the initial position. So again, that little triangle there is the Greek letter delta, and anytime we see that delta, it just means change in. So displacement or change in position is the final position of the object minus the initial position of the object. So we'll do a quick example here. It says the initial position of the object is -3, the final position of the object is +5. So that could be a number of things. There's lots of different routes that you could take to start at -3 and end at +5. For example, you could just walk from -3 all the way over to +5. And we would say that this object has a displacement of, well, the final position is 5 minus the initial position, which is -3. Okay? And 5 minus -3 is just +8. So we know, and I'm keeping the positive here, because I know that this object moved 8 meters to the right, or in the positive direction. I would also say the distance that this object traveled was 8 meters. If I went in a straight line from -3 to +5, I've traveled a total distance of 8 meters. But we know that's not the only way that this object could have gone from -3 to +5. For example, if there were multiple steps taken, this object could have gone from -3 over to -5. Maybe it went from -5 over to +8. And then maybe from there it walked back until it got finally back to +5. Now, what's interesting here is the initial position, -3, and the final position are still the same. So the total displacement is still exactly +8. This object has ended up 8 meters to the right of where it started. But if I'm counting the total number of steps, it's no longer 8 meters. This object went from -3 to -5, which was a total distance of 2 meters. Then from -5 over to +8, which was a distance of 13 meters. And again, I don't care about the direction. I just want to know what's the total length traveled. And then from +8, it went over to +5, which was another 3 meters. So now my distance and my displacement are not the same. I've gone a total distance of 2 plus 13 plus 3, or a total distance of 18 meters. So we can see the difference in that measurement when we include the direction as a vector quantity like displacement, and when we don't include the direction for a scalar quantity like distance. So these are both lengths, but my vector quantity displacement included the direction. I ended up 8 meters to the right of where I started, so that's why it's positive. Okay? All right. 2 more new vocabulary words, speed and velocity. Speed is the rate at which an object moves, or distance over time. Now, if we're not traveling at a constant speed, then I would call this the average speed. So the average speed, and I'm just going to use AVG, and I'm also going to put a line on top of the S to show that it's an average speed. Okay, so that's how we indicate average. The average speed is just the total distance divided by time. Since distance is measured in meters and time is measured in seconds using base SI units, we would want to report our average speed in meter per second. Now, there are other ways that we can write speed, kilometers per hour, miles per hour, but the base SI unit for speed is meter per second. Okay? Velocity is the rate at which an object changes position with a given direction. So we know that is, if it's including the direction, that is a vector quantity. The average velocity is just the object's displacement over time. So the example that I gave of starting at my home, going to school, coming back to home, since my total displacement for the day is 0, my average velocity for the day is 0. And that just means that when you accumulate all the motions that I did and you include the directions that I traveled in, I have ended up back to where I started. However, my average speed for the day would just be my total distance. So I'd look at my watch and see how many steps I took divided by the total time traveled. Okay, same units again, because displacement is a length. It's also measured in meters. We would also measure velocity in meter per second, but we're going to include that direction. So it is a vector quantity, so we have to include the direction that's traveled. Okay, so that should be it. Those are 4 new vocabulary words: scalar, vector. We're breaking into those 2 groups, scalar quantities and vector quantities. We have speed, velocity, distance, and displacement. You'll do a little bit of practice with those to see the difference between those new vocabulary words. If you have any questions, don't hesitate to reach out. Thank you.